these two different drawings there. Here, each particle is kind of separated, independent from one another. And this would be an ionic compound. And here, in this particular case, you do have two atoms connected to one another, form a unit. This would be a molecular compound. So we do want you to get used to this type of drawing. And the current trend really is that when we describe chemistry, when we describe what happens in chemistry there, the textbook and the educational approach tend to use a picture because it's more visual. So sometimes when you take exams there, like the ACS exam, the standard exam there, sometimes you see diagrams there. Now you need to be able to differentiate between what is a molecule, what is a molecular compound, what is an ionic compound there. You need to understand the drawing there. So if you have, say, a black dot or a white dot, if they're connected to one another, that would be a molecule. But if you have black dot and white dot and separated from one another, well, that could be individual atoms and could also be ions there. So we want you to, we want to get you exposed to this particular type of drawing there, so that when you look at those drawings there, you will know, okay, this is represent a chemical reaction between two different types of atoms there. You form a molecular compound, or you form ionic compound. Okay, so talking about the covalently bound molecule, and we mentioned this yesterday. Okay, the number of valence electrons for main group elements, and that's very important. Now, if you know which group they're in, you know how many valence electrons you have. So the number of valence electrons equals to the group number. And this is something that needs to stay with you for the rest of your life. Every time someone asks you how many valence electrons for group 6A element, 6. Okay, and group number equals to the number of valence electrons. Why is this important? Well, we're talking about molecular compounds. They're sharing electrons. Well, sharing electrons, you got to know how many electrons to begin with. Okay. Otherwise, you know, if you don't even have a total count of all the valence electrons, how do you know how they're going to be sharing? How many do we have? So that's the thing that you need to remember. For main group elements, the group number equals to the number of electrons. Transition metal, different. We don't want you to worry about the transition metal right now. Now, if you look in your textbook in chapter 8, in the chapter that we finished, there was one periodic table with the name, with the symbol of the transition metal elements, with all the valence electron configurations given in that table. So the total number of electrons in their valence electron configuration, you add them together, and you will get, say, for nickel, one of the homework question they're asking you, how many valence electrons does nickel have? Well, you take a look at the electron configuration. It's 4s2. It's a total of 10. It's a 3d8 4s2. So 8 plus 2 is 10. But if you look at nickel, nickel belongs to group 8b. So there is no correspondence between the number of valence electrons and group number in transition metal elements there. But for main group elements, group number equals to the number of valence electrons. We will use this to determine the total number of valence electrons when we deal with what we call the Lewis structure later on, either today or Monday. Okay, so looking at hydrogen covalent bonding, what happens in a diatomic molecule? Well, hydrogen group 1A, each one has one valence electron. Okay, so hydrogen being a diatomic molecule, hydrogen has to combine with another hydrogen atom in order to be happy. And this is just like a human. When you're alone, you feel lonely. You just got to get another human being with you, another hydrogen atom with you. Okay, so what happens in terms of the valence electrons there? Each hydrogen has one valence electron. And hydrogen is group 1A. It's in the first period. The noble gas element in the first period is helium. Helium has 2 electrons all by himself. So hydrogen said, I want to be like helium. I need 2 electrons to be happy. I only have 1. How do I get 2? Well, let me find another hydrogen there. We share those 2 electrons. So this shared electron would make each of the hydrogen atoms happy. So in this case, this pair of dots, that would be the shared electron pair. We use a dashed line to represent the chemical bond. A chemical bond in nature is a pair of electrons. We're talking about the covalent bond. So when you have covalent bound molecules, they're the atoms together, hold together by a covalent bond there. Each dash in between two atoms represents a pair of electrons, 2 electrons. Okay, so that's what happened. That's what's happening there in terms of the covalent bonding. And we use a pair of dots to represent the covalent bond. We can also use the dash line. So these types of drawings, you will see, as a matter of fact, next Tuesday when we're doing the lab there, we're going to play with some of the models, the multiple models there. And when we ask you to put the two atoms together, well, you use a little stick connecting two different colored balls together. And that little stick, the dash line, represents there is a chemical bond between the two atoms there. Okay? The nature of that chemical bond really is the sharing of the electrons. But when you share the electrons here, between the two hydrogen atoms, you know there is a proton in there in addition to that electron. So the protons both bear positive charges there. When you put them too close to one another, they start to repel. So the positive charge in the proton here is being attracted to the negative charge here. Okay? And then, but the positive charge is repelling this positive charge. The same thing happens to the negative charge. They are repelling each other, but they are being attracted to the positive charge in the opposite in the other atom. So the distance between the two positive charges is what we call the bond length. How long is it? We can actually, in the laboratory, we can actually measure, not using a ruler or a caliper, but by doing calculation that based on the quantum theory they're talking about the probability, we can actually figure out what's the distance between the two hydrogen atoms there in terms of their each of the positively charged centers there. So there's an electron cloud around each of the positively charged center, and these two atoms will come together and they will form the bond. And so the hydrogen gas and the diatomic molecule, you have two hydrogen atoms connecting with one another by sharing their electrons with one another, so that they have the same noble gas electron configuration, 2 electrons, same electron configuration as helium. Okay, and so that's our first learning objective. We covered some basic information that we have already pretty much talked about early on this semester. And then the next thing that we're going to mention in detail is that what determines who gets what. And that has something to do with the term electronactivity. Now we gave you the definition of electronactivity yesterday. And so we will take a closer look, I should say, about the electronactivity, and be able to determine if a given molecule, the chemical bond in a given compound, if it's polar or nonpolar, based on electronactivity. So there are 2 new terms involved in there. When you're talking about covalent bond, we have a polar covalent bond and nonpolar covalent bond. How do we quantify what is a polar bound, what is a nonpolar bound? We'll look at that. We will look at the nature there, nature of the electronactivity for the atoms involved in the chemical bond there. We'll give you some guidelines on how to determine whether a chemical bond is polar or nonpolar. Okay, so talking about electronactivity, Linus Pauling, an American chemist who came up with this calculation, he assigned values and kind of arbitrary values based on how atoms reacting with one another when they combine together. They did a lot of calculation by himself and his research team there.